Hello, Max, NG7M, back for another video related to the RF kit LDMOS amplifier. And the last videos I made, I think, were related to the clamps that will be available on the RF2KS, the new version announced at Hamvention. Well, I've been obsessed, as you can see on the screen here. The title of this video is Unhealthy Obsession with BLF189XRA Cooling. So I thought I'd make this video. I've learned a lot, and disclaimer, first off, there's no reason to make any of these changes that you're going to hear me talk about today. I've tried a number of different solutions here. I've even tried to outguess Reinhard in his approach for the RF2KS, and at the end of the day I've returned back to Reinhardt's recommendations and the approach he will be taking with the RF2KS. And I had some good input and discussions on the side with some guys, and you know, I'd even convince myself to go one direction or the other, but in all cases I've returned back to using the aluminum clamps, which will be available for use on the the older B26 RF2K Plus, and of course they'll be installed on the 2K or the RF2KS version available from DX Engineering here in the States in kit form, which I forgot about the kit form, and then once FCC type acceptance is all complete, DX Engineering will be putting those kits together and calibrating them and shipping them direct to the US customers as the exclusive dealer. Anyway, back to the video here. The last couple of videos, I think one showed the clamps. I did some just kind of unscientific testing, just kind of anecdotal testing on using the clamps. Then I switched to liquid metal, the Cryonaut Thermal Grizzly liquid metal, which has been a pain in the backside. It works, but anyway, we'll talk about that later. The first thing I want to jump into here is, I think, what is the best solution if you're insisting on making a change to your cooling and going to the indium foil or thermal pads. And I know Reinhard wasn't planning on selling the indium, but I bought some from I think it was the Netherlands, and we'll talk about that a little bit here. But what I want to do is go through some pictures of what I think is a pretty good solution if you're wanting to jump through some hoops and make some of these changes. If not, your amplifier's working great, don't mess with it. Keep it as it is and have fun and use it and make a lot of contacts. So with that, you can see the topic here. It's July 30th, post 2019 Hamvention experimentation with LDMOS clamps, and I tried some copper clamps too. We'll talk about musings and findings. LDMOS set sacrificed for the team. So yeah, I'll have some pictures here. A couple LDMOS devices, and you buy them from DigiKey here in the States. That's about $450 right there. Your mileage might vary a little bit on the cost there, depending on where you get them. But anyway, we'll get into that. I'm going to minimize this. We're going to pull up some pictures, and I'll just kind of let the pictures lead me through the early part of the discussion here. And let's see here. Okay. All right. Those familiar with my website, we have a set of pictures here I'm going to go through. And this is my, as of this date, this is the way I would go. I ended up having to install a new set of BLF189XRAs, and these first pictures follow that progression to what I have installed today. And we'll do a test. I'll do a warm-up test, and we'll take a peek, and then I'll talk about kind of the nasty part of the equation where I tried a bunch of different solutions. So here we have, I don't know how I'd recommend this, but I polished the copper heat spreader underneath the RF deck PCB. As you can see, and you've seen that in some of my other videos. Just use a high-speed Dremel with jeweler's rouge and really buff those babies to a mere finish, and lapped out the machining. There were some machining marks. I think with the indium material, the foil or pads that you'll see here, I don't know that it's going to make that much difference, but it might. On my last set that I blew up to, I also polished the the bottom of the LDMOS devices. Not worth it. Not worth it. Just go with the, make sure they're clean and go with the, what comes stock with those, in my opinion. Here you can see a picture. This was my second round of installing the Indium pads, which I'll talk about later. And Reinhard was quick to recommend that you cut the Indium pads smaller than the LDMOS device. So this was my second go around, because in theory, right, the pad is going to, I don't know if it's a proper term, but there's cold or hot flow on the indium where it compresses, right, and will, not very scientific, but squish it out a little bit, and there's concern about that creeping up the sides and shorting out against the source or the gates on the device. So my approach with the pads, if you order these, not from Reinhard, and I've posted that on the website where I bought them. It was about $15 US shipped, and it took several weeks to get here. But the material comes with a clear plastic coating that comes right off. I cut the indium foil with that material on with just some sharp scissors, and then carefully kind of cut out the areas where the holes go. And this picture is showing a high quality, this leads to a whole nother discussion, this is a high quality torque screwdriver, okay? Right here you can see the one in the picture. And if you're careful on eBay, you can find one of these for probably around 40 to 50 bucks. And so if you look at the spec on the 189s, you'll see that they have a spec of about, off the top of my head, I think it's around 0.9 Newton meters of torque, and that equates to around 6 to 7 inch-pounds of torque, which this torque screwdriver is based on inch-pounds. So this one goes down to 6 inch-pounds, and the next setting up is 8 inch-pounds. I actually use the 8 inch-pounds of torque when I install the devices. You can see in the picture here that because I was installing new LDMOS devices, you'll want to be very careful, and I installed the LDMOS device carefully on top of the indium pad that you saw in the previous picture, and then actually installed the clamps on to hold those down before I soldered the source and gate tabs to the PCB. So I think you want to be careful with these torque screwdrivers too, because when the torque setting trips, right, it snaps, and it causes a lot of I mean, if you've used one before, it's kind of, there's a snapping sound, and I don't like the idea of that jolting the whole device. So I was pretty careful not to let that snap. Maybe I'm overcautious there. And there's been a lot of discussion on proper handling of the LDMOS devices too, which you should do. Avoid static discharge. So again, all the specs are out there from, is it aptly owned as the manufacturer. So if you're going to use these aluminum clamps, my earlier videos I just did it by hand, and I know a lot more now. What I know now is you want to be very careful to not clamp these too tight, and I'll show you later why on the devices that are ruined effectively, because I tried all kinds of different things. So I clamped them in. Another shot of the screwdriver, and here's the other one just set in, and you can see it's right on top of the indium foil, if foil is the right term, or the indium material. It's interesting, that indium material. Let me show you real quick here. It's like impossible for me to do a short video here. Okay, now I've got 2 videos going, and I've got that pad right here. I put it inside a little case that came from Thermal Grizzly. rather than keep it in the... So here you can see the pad on that clear plastic sheet. But what's interesting, clearly, I mean, the atomic weight of this indium stuff is pretty high because you know, for as thin as it is, you can kind of feel the heft. But you'll want to be careful with it, obviously. And I might come back to that. So here you can see the second LDMOS device carefully aligned, you know, within the PCB before it's soldered on, and you can see the indium foil or pad, you know, I don't know what the proper term there is, underneath there, you know, right where the little stainless steel bolts will go in. And to continue on, this is another shot. It looks like I've got this side soldered, this side not. You know, there'll be a link to all these pictures as usual in the description of the video. And here's a shot before I soldered this side. It looks like the order here might be a little backwards. And another shot with all the soldering done. And with a little cleanup with, you know, I use denatured alcohol, clean all that off. Which you could leave the flux on. It's just going to go yellow over time. Be careful if you're using denatured alcohol. You don't want to, you know, get crazy and let it get underneath the LDMOS device. Just be real careful if you're cleaning that up, if you end up soldering a new set of devices in. A couple more shots there. And okay, here is a NG7M custom mod. You know, I had some discussions with Reinhard about the actual clamps being only on the ceramic here. I'll talk a little bit more about that later too. And also with some other guys offline. But, you know, ceramic obviously is a great insulator, but it's amazing how much heat still comes up, number one, likely through the ceramic, which is hollow. You'd think, you know, at first I thought this was like a solid piece of ceramic on top of the, you know, the silicon or the devices, however that's manufactured there. But the clamps, right, are straight through. So with these clamps, the only pressure applied is directly from the ceramic. So hence, be very careful with the torque specifications. Come to find out, I think that's very important here. If you're going to do this yourself, either be comfortable doing things by hand or get yourself a good torque screwdriver and follow the specifications within 1 or 2 inch-pounds of torque. You know, close to that 1 Newton-meter pounds of torque. Another shot here. Okay, here's another, what I was going to get to and I alluded to earlier. I took a older fan I had laying around. This is a AMD, actually, CPU fan from years ago that I never used. It's 70 millimeters by 15 millimeters, and it fit in here nicely. There's a bracket on the back of the fan that butts up nicely against the cooling fans that I added, or fins that I added. Oh, so I just ordered, I'm going backwards here. I ordered these little heat sinks off of Amazon. You know, find something you like if you want to go this far, which you don't need to do, but I did. And there's also some good thermal heat sink glue that's really strong that I glued these onto the top of aluminum. I mean, it would be tough to pop these off at this point. So back to the fan. You know, I put the fan on, and I was shocked at the difference this made, and I liked the idea, especially on the design of the S version, which we'll see at the end of the year, where there's a direct flow of air flowing across the PCB and out the back. I think in that final version, I'll talk a little bit about the airflow that I've seen here, but I'm getting, you know, a high amount of air now over those LDMOS devices. And so I'll go to the next picture here. Here's another shot of the zip ties. I made sure these zip ties could handle, I mean, easily they can handle 60 to 70 degree or 70 C heat before they melt. So they're just loosely, you know, strapped underneath the front of the clamps there, up over the top, and I dremeled in some slots here on the fan. So it's not, you know, ugly, but it's not super pretty either. But it's a nice way to hold the fan in here, butted up against the bias jumper pins and the multi-turn pots for the bias adjustment. That's another video I should make. I should do a video on bias adjustment. Another shot there. Okay, another NG7M little mod here. When I first started using this fan, I did a lot of testing with the RF deck up into the 50C range, and I was shocked when I lift this. I was just sitting on there at first. When I move it away from the fan, how much the heat would just jack up within 10 seconds. 5C, and it got me thinking about, I've never paid much attention to the thermal resistor device that is being used in the design, that Reinhard used in the design here. And that little device is right here, and off the top of my head, I think it's an 18D20 package. There's different packages that are real common in thermistor devices. This is a little more sophisticated package. And when this fan was blowing air across that device, it artificially cools it down, so you're cooling down the device, but the the copper heatsink, right, you're not getting a true representation here. So my solution to that, where I'm now blowing a lot more air. By the way, this is quiet too. I really don't notice a noise difference with this fan, even when it's when you're up. I think the max fan speed's around 55C or 56C, but so this is if you're going to be blowing direct air here, you don't want to be cooling the thermistor package artificially. You want it to be reading the temperature that's coming up through the copper heatsink and through the PCB to the package. So I covered it up. I took a little plastic cap I had, I sanded it down, I took a little RTV material and just kind of sealed it up over that device, and it made a big difference, right? So when there's air flowing over the PCB, you're not artificially cooling that device and causing the fans to slow down to some degree. And it's probably going to reach an equilibrium regardless, but it was easy to do, and it made a big difference, right? I thought the fan was doing a lot more cooling than it really was at the end of the day, right? Because there was no way it was cooling down as fast as it should, just from the heat transfer from the LDMOS devices through the copper heatsink over to the thermal resistor. Again, the air was cooling that thermistor off way too quick. Hopefully that makes sense. So here's a close-up of that. It's just sealed up, keeps the air from cooling the little package there, and so you're getting a truer representation of the heat coming up through the copper and copper heat spreader and the PCB. And in hindsight, if I ever lift my PCB up again, I'm going to make sure and put some good thermal paste under this area of the PCB, right? Because you want that package to be getting the best representation of the heat of the copper heat spreader. And another shot there. Here's a quick shot of the splitter I put in place. So I'm using the top header here. Again, I don't think there's a problem with the additional current draw. That fan is rated at 0.2 amps at 12 volts, so I haven't seen any issues with it so far. Just to kind of hold things in place, I put another ferrite around that Y splitter. I don't know if you can see the detail here, but this is just a commercial little Y splitter cable. And also, if you use some fan that you have kicking around like I did, make sure you get the polarity right on the pins, etc. Right? You've got for the high-speed voltage, you've got the center pin is positive and the left pin is negative to ground here. And so make sure that passes through the splitter, obviously, to the fan you're using, and the fan's spinning the right direction. Another shot of that. I'm only using 2 pins right in the splitter. These other pins are not hooked up to anything, so there's no connection there. Here's a top view of the whole setup, and it just barely fits under the case, so there's maybe 1/8 of an inch, 3-4 centimeters between the case top and the fan, and it holds it down nice here, and it's quiet. Here's a picture of the fan actually spinning. You can kind of see through here to the back where these brackets on the other side of the fan just kind of rest right against the edges of the heat sinks that I glued to the top of the LDMOS clamps. So, pretty cool. I mean, I like the solution. Another shot, and that's all I had here. Let me go back a couple. Let me talk about the airflow here. If anybody's played around with the airflow, I know Reinhard's done a lot of testing on this on the original B26 RF2K plus, you'll find that the draw, so this is the back of the amplifier, the front of the amplifier obviously, the airflow with the case on top and the front panel in place, the default front panel with the slits at the bottom for the air draw coming into the amplifier, the fans are going to pull enough air through to where you're drawing air from the back of the amplifier through the intakes of the back of the amplifier. So the airflow across the top of the PCB RF deck here is actually flowing from the back to the front, and it's drawing air in the intake and then back out the back of the amp. So you may be getting a little hot air being redrawn in here if you have the back of the amplifier close up to a wall. And I really wasn't trying to pull air, cold air from the front of the amp in through this my little custom fan solution here. I wanted to increase the airflow over the top of those LDMOS devices and blow air through the transformer here, which it does a great job. So I don't think there's any issue with air. There's, the air is getting drawn in the back, not a lot of, cubic feet per minute or whatever, but you're taking that fresh air that's coming in. It may be contaminated a little bit by the exhaust off the back of the amp, and you're blowing it over the top of those devices and keeping the transformer cool. So, for those of us that want to hack up the amplifier and do some experimenting, I'm pretty happy with this solution. So again, kind of going to the end of that's the last fan shot I have here. So let's actually fire up the amp here and do some testing. And then I'm going to go into the nasty portion of my musings, and I'll show you some nice pictures of what the LDMOS devices look like with this ceramic removed, which is really interesting. So I've got VNC hooked up to my amplifier here. We're going to make this nice and big. I'm just kind of let's go another size up. Oh yeah, that's big. How about if we make me small here, a little smaller. And I will get my LP700. Oh, there it is right here. Okay. All right, so you can see I'm on a 40 meters, 7 megahertz, kind of down in the CW portion of the band. You can see that the temperature being reported to the controller is 32C, and because I heated this up earlier this morning, and I think the ambient temperature, right, it's the end of July in Utah, it's probably in the low 90s outside. It'll maybe 93, 94, maybe up to 95 today. So it's a hot day. I'm in my shack. I think the ambient temperature is probably around 76 degrees Fahrenheit. I'm terrible on the translation. Sorry for the smarter portion of the world that uses the Celsius. So centigrade Celsius. So it's not cold in here by any means. If it was the middle of winter and it was 68, 69 degrees in here, the things are going to be a lot different. So I need to double check that I'm into my dummy load here. Let's see here. And I am on the dummy load. And I'm just going to key the amplifier up here, and we're going to watch this baby heat up. And I don't recommend doing this. I know a lot of guys are shy about this. I've got a new set of LDMOS devices, and hey, it's kind of fun to show what you can do here with the correct setup. So we've got the Indium pads. I think this is about as close as you're going to get to the S version of the RF kit, and this will give you an idea of where you're at. I think I'll drive the amplifier up to about 800 watts, 750, 800 watts, and we'll see how long it takes to get up, to 60 degrees or something like that. And we'll let you guys be the judge of my solution here. And it'll be interesting to see if you can hear the amplifier too on the microphone. I actually have the microphone on the left side of my monitor over here. The amplifier is over here. I don't have a camera on that. So there's a half watt of drive without putting the amplifier into operate. So with a half watt of drive, I'm getting 143 watts, and so we should see the we'll see how long it kicked up to 33 degrees here, as you can see. And so I'm going to drive up the amp, and here, let's just go up to a kilowatt for a bit. And we'll see the temperature increase here. So those fans will kick on around 42°C. And here, let's just see what we're getting, how much drive it takes to get to 1.5 kW. Okay, so there's 1.5 kW, and that's 17 watts of drive with my setup and the bias I have set. So we're back to 1500 watts of drive. We're up to 45°C. Now, just for fun, we're going to, put it down to, let's go down to, let's say 750 watts, right around there. And I don't know if you can hear the amps there. Here, we'll put it right around there, because as the devices heat up, they're going to be a little less efficient. And so for that amount of drive, it's taking 3.7 watts roughly, depending on how accurate the LP700 couplers are, and its calibration. By the way, I have a 13 dB attenuator pad in, kind of the stock one that Reinhard typically sells. I think that's a good compromise between low drive and touchy output based upon your drive. So here we're back to channel 2 here. We're still at 750 watt range. We're up to 54°C. And you're going to see this temperature slow down. So clearly I have my new little NG7M AMD CPU fan mod in the amplifier. The case is on, the front panel's on, it's in normal operating mode. And I'm right around 6 foot-pounds of torque on those LDMOS devices. And I'm just kind of making stuff up to talk about here. Don't buy one of these new, they're about $350. Buy a good one though, I think, if you're gonna get crazy like I have playing around with this, doing experiments. We dropped a little bit below 750 watts out, and we're at 58°C. So, this is 100% duty cycle. Let me drive it up to a kW. 60°C. Drive it up to 1500 watts here. So we're at the max fan speed at this point. So there's 60°C, 1500 watts out. But go back down to, technically, depending on the power you're driving, you'll actually generate less heat at a higher wattage output, believe it or not. Or so I've read. I don't know the science behind that. But. So now just back down to 750 watts here. Pretty much pinned at 61 degrees. It's pretty warm in the shack here too. There's 62. Go back up to a kW. 1 kW. 63. And back up to 1.5 kW. I know a lot of guys are paranoid about this, but based on the rating of these devices, it should be perfectly fine. Here's 1.5 kW. 63 degrees. Still losing a little power here. 64 degrees. You'd never do this under normal operating, right? Like I've demonstrated in the other videos. I think we'll call it good at 65. There, we touched 65 degrees. So I'm going to unkey, and then we'll watch a little bit as it drops down. I think let's minimize this, and we're going to get into a discussion about some of the other things I tried here. I'm going to keep this down, way down here, so you can see down here the current temperature as that drops down. Let's go back to the pictures, and I want to talk about, and we're going to show you some stuff here. I did a couple of different things. Let me move that up here so you can see the temperature. Whoops, sorry. So we're down to 56 degrees, so just keep an eye on that down here. And I'm going to turn the other video on. So my other video, I spent the money and I jumped through the hoops with the liquid metal stuff, which I've used over the years with CPUs. I wouldn't go, it's not worth the mess, you know, if you end up making changes and getting the amount right. And it works really well, but I think over time the performance degrades of the liquid metal here. I can't recommend it. I wouldn't use liquid metal with this particular configuration. We're down to 50 degrees C, by the way. And here's another here's another thing I tried. I mean, I jumped through all kinds of. This is another product by Thermal Grizzly. They actually have some carbon thermal pads that are conductive, and this is where I was trying to outsmart Reinhard. I thought, you know, let's use this carbon fiber pad. It's made to be reused in the CPU world, so it's nice, right? There's no mess. You cut it. I tried it underneath the LDMOS devices. The resistance to ground was higher. It worked, but I wasn't happy with the resistance to ground. It, you know, it didn't make me feel very comfortable. And during the time I was messing with, I was taking the clamps on and off and pulling them up and, you know, trying this material. I also tried putting this material between the clamp and the LDMOS device. I always assumed that the ceramic was like solid on those devices. Well, it's not. By putting, you know, a spongy thermal pad between the device and the LDMOS devices, which I tried, I mean, it worked, but what was going on was I was cracking the ceramic on top of the device. And there was a time when I was applying too much pressure with the clamps too. So again, you know, let NG7M spend the money here. I wouldn't mess with this. It's an idea, and I wouldn't put anything between the clamp and the device, the ceramic. Go with Reinhardt's experimentation and his recommendation. Use the clamps directly on the ceramic devices with the proper torque. And believe it or not, you can actually buy versions of the devices that don't even have the little ears on them, the tabs. Right? They're designed to either be soldered down or clamped down to heat spreaders. So, you know, there's probably some debate around that, but if you keep that torque and pressure within the specs by Amplion, I think it's the best solution. Okay, so enough of that. There's another. Here's their non-conductive stuff I used with some copper clamps that I bought from Russia, which I'll show you if anybody's still watching at this point. So let's talk about the copper, my foray into the copper clamps. So I bought, let's see, I need to shut off that other video. Let's see. So I bought, and this was an interesting idea, and this is where I thought I had outsmarted Reinhard. But these clamps, I think, are a good solution, but I'll show you why they ended up not impressing me long term, especially with the Indium pads. Here you can see I glued on heat sinks here too, and I had to grind the ends of these, and I'll show you in another picture, to make sure they were clearing the PCB. I was a little bit worried about that, right, when they were clamped down. And the tendency, if I was using these copper clamps, there's a gap underneath them between the ceramic and the heat sink, and I even tried putting like a compressible pad underneath here between that and the ceramic, which again ended up cracking and breaking the devices, which I think led to the destruction of the devices, and we'll get to those pictures. So yeah, I mean, it's up to you. The idea here is pretty good, right? You're going to get, you're going to get heat. Let me go to the next picture. You're going to get heat drawn up through the tabs, up through the copper devices, and hence me gluing on the heat sinks. But there's a lot of heat clearly coming up through the ceramic here. And I even tried, cutting, not indium, but I cut that thermal grizzly carbonate, or whatever it's called, stuff, and put on here. And I tried a third-party stuff too that I found on Amazon that was a I can't remember. It wasn't nearly as conductive as the carbonate was, as far as electrically conductive. But my conclusion, why I didn't end up sticking with the copper clamps, was, I will show you here. If we go out of directory here and we go into, let's see here. These are the pictures from my last videos. And yeah, these are pictures from my last videos. Copper clamps, we got those covered. Okay, this is where I wanted to get to. Okay. All right. Here's the two devices that I sacrificed here. 225 bucks US a pop. So you can see the ceramic ended up getting cracked primarily because, number one, I was playing around with way too much torque early on with the aluminum clamps, and I was also playing around with putting thermal pads, two different types, actually three different types of thermal pads underneath here, thinking that was going to be a better heat transfer using the copper clamps. I mean, I tried all kinds of combinations, but this one was in worse shape here as far as the cracked ceramic, and it's amazing how much space there is between the ceramic and the actual devices underneath here. So it's kind of cool to see inside here. But I had to actually pull the ceramic out here and bust it here. It was cracked, just because I wanted to, at this point they're destroyed, so I wanted to see what they looked like on the inside. So here is my reasoning for sticking with Reinhardt's solution and the aluminum clamps across the full top of the ceramic. With the copper clamps, first of all, I clamped them down at more than 0.9 foot-pounds of, or inch-pounds of torque, more than the 0.9 Newton meters of torque. And it's amazing to see how the ears and the center of the device pressure differs. So you can see this is leftover indium material here that I did get a better or a lower resistance to ground when using those copper clamps, but you can see that the inside of the device isn't compressed down on the indium and the heat spreader nearly as much. And so I think the theory there from Reinhard is that is causing some of the failures that potentially have been seen. I'm not sure. But after all was said and done, I went back to Reinhardt's solution, and I'm sticking with it. That's the long story of this video. So here's a good shot of how much space there is in between the ceramic and the actual LDMOS devices. It's pretty mind-boggling how the device can take such low power and with the right amperage and voltage, right, 50 volts at X amount of amperage, it can take that low signal and amplify it the way it does. It's pretty cool. And then you put two of them in concert, right? So here's another good shot. Here you can really see how much space there is between the ceramic and the actual individual devices in here. And it's amazing how hot, how much heat still is transferred upward. Clearly most of the heat is transferred down into the heat spreader. And another shot there, you can kind of see You know, I don't know if this was part of the failure or not. You can see the way that the connections are made between the source and gates are with these small teeny tiny wires. It's really interesting how the manufacturing process is there. So that's it. That's it, guys. We're back down to 37 degrees here, and I think I've done enough rambling. The next video I want to do is on bias adjustment, and I want to do another video on adjusting the SWR bridge. I think the documentation that's out there now, it confused me until I finally got my head wrapped around it. The correlation between the pots that are in the SWR bridge. If I get motivated toward the end of the month, I'm going to take a couple weeks vacation here, week and a half. Maybe I'll get motivated again at the end of the month to do a couple more videos. So if you liked this, you know, give me the thumbs up. I think that's about it. I had a couple other tabs open. There's DigiKey, $225 for one of those devices. My videos. I think that's it for now, guys. Have fun with the amplifier. Get on the air and use it. And I hope to hear you on the air. I've worked a lot of guys with the RF kit amplifier now, and so that's always fun to make that connection. Send me an email. Give me the thumbs up. But comments, rational comments. You know, if you're not willing to do this experimentation like I'm doing, then if you're going to make ridiculous comments, they're not going to show up on the page. This is supposed to be fun and a learning experience. I'm certainly not a you know, master's degree EE engineer. I just do this for fun. I'm a software engineer. So thanks for watching, and I'll end with a joke. How many software engineers does it take to change LDMOS devices on an RF kit? How many software engineers does it take? It's not possible because it's a hardware problem. 73, guys. Have a good weekend.